Let's begin with a word of prayer. I'll start. Dear Heavenly Father, we thank you for this day. I thank you for these students. Just ask that you'd guide our steps today, Lord. We thank you that you're a good and awesome God, and we thank you for your mercy to us each and every day, Lord. In your name I pray. Amen. Okay, so I think I owe you guys maybe an example or two more about parabolas. Yeah? So let's talk about how to find the how to graph a parabola. And so just to summarize, we have three major forms: y equals ax squared plus bx plus c, right? The so-called standard form. We also have y equals a times x minus h quantity squared plus k, right? The so-called vertex form of the parabola. And then, not last but certainly not least, we also have the X-Intercept form of the parabola, right? So if you have any one of these equations, it has different information, right? From the first one, if you have this, what does this tell you? The first one doesn't tell you much, right? First one tells you what? C is equal to the Y-intercept, right? So it gives you that much, right? This one tells us the vertex is where? H comma k, right? Vertex is at H comma k. This one tells you that R1 comma 0 and R2 comma 0 are what? They're X-intercepts, right? Now, there are strings attached to the third form of the parabola. When is it possible to write the equation of the parabola like the third one? It's not always possible, right? This is only going to be, R1 and R2 are only real numbers if what? Only if b squared minus 4ac is greater than or equal to 0, right? Otherwise, you can't do that, right? Otherwise, it's a prime polynomial, which means that it doesn't cross the x-axis, right? It doesn't have x-intercepts. And what else did we figure out? Just to reiterate, we know some things, right? We have formulas. We know that R1 and R2 are equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a, right? That's the quadratic formula. So the quadratic formula tells you where the x-intercepts are. It's not usually the case that this is the right way to find them, but you can, yeah? What else do we know? We also found formulas. We found that h is equal to minus b over 2a, right? But we also learned that, or I'm going to tell you, that it's the sum of the roots divided by 2. In other words, the vertex, the x-coordinate of it, has to be at the average of the roots, all right? And we also had a formula for k. I'll put it over here. K was equal to, what was it? It was c minus b squared over 4a, if I remember right. Is that right? Did we derive that last class? I completed the square at an arbitrary one. Yeah? Yes, no, maybe so? I haven't reviewed the transcripts, so I don't remember. I've taught this class like 3 times since I taught your class last, so I'm a little fuzzy.
No, I don't think
Where?
we did anything like that.
We didn't derive this? Ah. Okay.
Oh wait, never mind, we did.
Okay, good, because I don't want to put you through that again if I've already put you through it, you know? But the way I derived that was just to complete the square on the arbitrary quadratic, okay? So these are formulas we know. These can guide our steps, yeah? Let's look at an example. So now more often than not, when I work examples, I don't find myself using the formulas as much as I just find myself doing algebra. So if I want to graph y equals to, oh, I don't know, minus 2x squared plus 4x minus, oh, I don't know, 6. All right. How would you graph such a thing? Well, what I do here is I start by factoring out the minus 2. Factoring out minus 2. So what can you tell me about this graph? It's going to open down, right? It's got a negative a. Whenever a is negative, it opens down. Whenever a is positive, it opens up, right? There's that. Now, we could complete the square here, and maybe it's useful to do that. Let me go ahead. I think we could also factor. Oh, no, we can't factor. Let me complete the square. I thought I could factor, but I think I just tricked myself. So let's not do that. Complete the square here. We have x minus 1 quantity squared, yeah? And then I have to subtract 1, and of course I have the plus 3, right? So what is that? That's minus 2, big parentheses, x minus 1 squared plus 2. Now I got to be careful. That's not in any of the formats here, is it? It's not, right? So to put it in the vertex form, what do I have to do? I have to multiply the 2 back through. Multiply that, well, minus 2 back through. So what I have is I've got minus 2 times x minus 1 squared minus 4. All right? Now, my formula is in vertex form, right? So now this is in vertex form, where my vertex is what? Just look at it. It's got matching the pattern, right? My h is 1 and negative 4. Now you can reproduce those numbers using these formulas if you want, right? Like you can check minus b over 2a. What is it? Minus b over 2a is what? It's minus 4 divided by minus 4, which is of course 1, right? So my formula for h does check what we found with completing the square, yeah? And you could also check the k with the formula as well if you wanted, but I'm going to get to the point here. So now we can graph. We have everything we need to graph. Yeah? So let's see here. The vertex is at, oops, poor planning on my part. Almost everything interesting pretty much everything interesting about this parabola happens where? Like south of the x-axis, right? So, fix that. So, let's see here. The vertex is at 1, comma, minus 4. Like here, all right? Right? And what other point do we know on the parabola? Can you guys tell me? So looking at the formula, what's another point on this parabola? I know it's early. You can do it though. Somebody help me.
You could do like negative 2, 0.
Negative 2, 0.
Just like with the negative 2 there.
No. Well, no. Negative 2, this thing would be kind of big. Like if I plug in negative 2, you're going to get 3 squared here. I mean, you get minus 3 squared, which is 9 plus 2, which is 11. 11 times minus 2. So at minus 2, it's at minus 22, which is like here. But that's okay. Yep. 0, -6, right? So your point is right here, right?
So you're using the first equation, not the vertex one?
Yeah, right. So go back to the first equation. There's low-hanging fruit right there. Y-intercept is -6, right? And once you know that, you know the vertex, right? So what do we know about the parabola? It is symmetric, right? It has a line of symmetry about the vertex. So if I can graph the parabola from here to here, right? So there's this y-intercept here, right? But that means that there's a symmetric point over here as well, right? The same distance from the vertex, the vertical line there. So the y-intercept is, like you just told me, 0, -6, right? That makes this point over here 2, -6, yeah? And so we got that, and then we just keep going. And of course, you could add another point if you want to be more accurate and then reflect it. But there you go. That's the graph. Y equals -2x² plus 4x minus 6. Now, x-intercepts are no help for this graph, are they? Because this is a prime quadratic. So there's no x-intercepts at all, right? Let's do another one here. Example 2. Let's graph y equals to 3x² plus, I don't know, I'll get it eventually here, 9x plus, well, let's not say plus, let's say, yeah, we'll find plus 1. All right, so to graph this, I got to factor 3 out. Yep, so I factor 3 out. That gives me x² plus 3x plus 1/3, yeah? Then what? Then I need to complete the square, yeah? So, because this does not obviously this does not factor nicely, yeah? That's fairly obvious. So this is 3 times x plus 3/2 quantity squared, yeah? And in doing that, I have to subtract the square of 3/2, which is 9/4. And then I add the third that's still there, yeah? So I complete the square. And it looks like my overall number there is negative. If we use 12ths, what do we get? Like I can put quarters and thirds into 12ths, right? So 3 times 9 is -27, and 4 times 1 is, well, 4. So -27 plus 4, I believe I get -23. I think that's 23/12 if I did it right. Do you guys want to confirm or deny that? Let's see here. -9/4 plus 1 divided by 3. Yeah, -23/12. Let's see here. So then what? Well then, to see what the vertex, I mean, there's a couple different ways we can go here, right? There's a couple different paths to take here. One path is to factor it, right? Like we talked about on the test 1. So factoring here, you have 3 times x plus 3/2 plus the square root of 23/12, right? X plus 3/2 minus the square root of 23/12. So we could factor it, all right? And just for the sake of our graph in a bit, what is 23/12, square root of 23/12 in terms of a decimal? It is about 1.38. So 1.38 plus 1.5, which is 3/2, of course. So this is, roughly speaking, 2.88-ish. And that one is I think Wait a minute. Why am I not? Oh, I'm a dummy. 1.5 minus square root of 23 over 12. That gives me about 0.12-ish. All right, approximately speaking, of course. And so what's that say my R1 is? Where are my roots? So X-intercepts where? Minus 2.88, comma 0, and minus 0.12, comma 0, right? Because if the numbers there are 2.88 and 0.12, we have to look at the negative of those numbers to see where the X-intercepts are, right? Like if you've got X minus 3, that means your X-intercepts at 3. Okay, so fine. That tells us where the X-intercepts are. Where's the vertex? So to see the vertex, I'm going to come back to this step right here, yeah, and I'm going to do, what I'm going to do is I'm going to multiply that 3 through, and I'll keep it on the first term, of course, 3 times x plus 3/2 quantity squared. And then when I multiply 3 through there, I get minus 23, what's 3 over 12? 3 over 12 is 4, so I get minus 23 over 4. Right, so that tells me that the vertex is where? Vertex is at minus 3/2, comma, minus 23 over 4. Now, of course, if you don't like my way of doing things, what else could you do? To find the roots, you could do what? You could fall back and use the quadratic formula, right? And you could use these formulas I found for you for h and k to find the vertex as well, right? Like, for example, here, let's double check the 23 over 4. So just check on k. I have a formula for it. It was c minus b squared over 4a. What is c, b, and a here? Well, c is 1, yeah? And what's b? b is 9, right? So minus 9 squared, which is 81. And then 4 is 4. What is a? It's 3, right? So 4 times 3. So what we got there is 1 minus 27 over 4, right? Which is 4 over 4 minus 27 over 4, which is indeed minus 23 over 4. So it checks. 81 is 3 times 27. That's why I canceled the 3's. But, okay, anyway, we have all the information we need and more to graph it. Yeah? So let's do it. Let's graph this thing. The graph looks something like, let's see, so we have X-intercepts at minus 0.1-ish. So let's see here, let me make this 1 minus 1, 2, 3. All right, so my X-intercepts are where? Minus 0.1, it's about here. And also at minus 2.88, which is about here. Right? And where's my Y-intercept? My Y-intercept is where? So it's, again, sitting right here for us to see, right? This 1 gives me the Y-intercept. The Y-intercept is 1. And my vertex is where? So in decimals, what is this? This is what? Like minus 1.5, comma what? 23 over 4. What's that? Well, if it's 24 over 4, it'd be 6, right? So that's minus 5.75. Which is, you know, a bit down here. So there's my 4, 5. Let's see here. So let me try to draw the axis of symmetry here at 3.5. Yep. I'm trying. Anyway, so the vertex is on there somewhere, about right here, right? I've got this point, I've got this point, I've got that point, so I will try. And then if I did it right, it should be sort of symmetric. Anyway, I'm never quite successful in graphing it very pretty. If the graph is this size, you know, you do better in graph paper and all that. But there it is. And of course, to be precise, this is at minus 3/2 minus the square root of 23 over 12. And this x-intercept is at minus 3/2 plus the square root of 23 over 12. If I want to put the exact x-intercepts, that's what they are. And the vertex is where? Right here, minus 3/2 comma minus 23 over 4. So, any questions? So we can graph parabolas pretty carefully if we do what? If we keep track of how to complete the square, find the vertex, find the x-intercepts if you got it, keep track of the y-intercept, put all these things together, you got a pretty decent looking graph, all right? That's all I have to say about that, actually. So we're moving on. Our next topic is polynomial graphing, all right? So I will dive headlong into that here next. So I have bad news and I have good news as it pertains to polynomial graphing. The good news is that we've kind of done this before. The bad news is about half of you don't understand how to do it. So that's also kind of good news because it means you're going to get a chance to review something that a lot of you had go a little bit sideways on test 1. So this is an opportunity to fix it before test 2 for one thing, and obviously before the final for another, because I will, and so this is something I think I may have said in an announcement, I can't remember, but I will replace your test 1 grade with your final exam grade if it's helpful. So like if you absolutely failed this first test, it's not over for you. You can replace that with a grade of A. If you make an A on the final, great. It is washed away. I do not care. I mean, I care. I'd rather for you to make a plus on everything and just not be worried about the course. That would be, I prefer that. But most of us are still learning, right? So it's a process. I'm far more concerned with what you leave the course with than what you have in the middle of the course, right? So there's always a second chance right up until the final, after which point there's no second chances. So, because it is, as it says, the final, right? So anyway, so polynomial graphing. So what I'm trying to tell you is all is not lost. If you can figure out what went wrong and adjust, there's still hope, because the final exam is comprehensive. It will be very, very reminiscent of things that happened before. Probably different numbers, different functions, but same concepts, yeah? So. Okay, so polynomial graphing. What is a polynomial to start with? That's the first thing we need to address, because just because I say the word polynomial doesn't mean you know what I'm talking about. So polynomial has the following form. F of x equals an x to the n plus plus a2x squared plus a1x plus a sub 0. Okay, so this, if your function has a formula like this, it's called a polynomial. All right? And if a sub n is not equal to 0, then the degree of the polynomial is equal to n. All right? And fine, so that's just the terminology, all right? The numbers, a1, a0 through a sub n, these are called the coefficients of the polynomial, right? And this is its standard form. In the same way that ax squared plus bx plus c is the standard form for a parabola, right? So what we just got done doing is really studying how to graph the n equals 2 case, right? The n equals 2 case is a parabola. So now we want to take it up a notch and do it for arbitrary n, all right? So here's how we do it. Well, I'm not quite there yet, but there's a theorem that guides us. So the theorem is this. The theorem is called the factor theorem. Factor theorem. And what does the factor theorem say? It says the following. It says if f of x is polynomial, right? If f of x is a polynomial, then the following. F, well, rather, x minus c, all right, is a factor of f of x, all right? So this is true if and only if f of c is equal to 0. All right? But that's true if and only if what? C comma 0 is X-intercept of y equals f of x, right, of that graph. So there's a one-to-one correspondence, right, between factors of the polynomial and x-intercepts of the graph. What that means is if we can completely factor the polynomial, then we have all of the x-intercepts at our fingertips, right? Now there's also a much smaller theorem, right? A much smaller theorem, which is that f of 0, which by the way is equal to a sub 0, is the y-intercept of the graph. Yeah? So, hey, we were just doing that a second ago here, right? For the case of the quadratic, right? For the parabola, c was a sub 0 in that previous thinking. Yeah. Yeah.
So what's with the ellipsis, like the 3 dots, like in the top formula again? Like what's the symbol?
Oh, this just means it goes on.
Okay.
So it's just, yeah. That pattern continues. There's n of them. I don't know what n is. N could be 10. It could be 7. So we have that. And then there are 4 cases, all right, that we should watch out for. So here's the 4 cases. I'll draw each one of them. So the one is, it looks like this. It looks like that. It looks like this, or it looks like that. So here we have, you know, degree f of x even. Here also we have the degree of f of x even. Here we have the degree of f of x odd. And here we have the degree of f of x odd. All right, these are the 4 different cases. But to bifurcate the cases more properly, I mean to separate them, I have to tell you which one's which, right? So what makes this one and that one different? So here we have a sub n, leading coefficient positive, leading coefficient negative, leading coefficient positive, and finally leading coefficient negative. I'm using this term, leading coefficient, right? Here's then this is, by the way, a sub n is quote unquote leading coefficient. So for the parabola we were just graphing, the big A was the leading coefficient, right? And whether that was positive or negative determined whether the graph opened up or down, right? So these pictures, this is what the graph of what we're doing should look like from I tell my classes, this is what it should look like from like 1,000,000 miles away. If you ignore the X-intercepts and all the local behavior of the function near the origin, this is what it should grossly look like very far away. We should be able to double check our answers with these patterns. Okay? And now for the method. So here's how we're going to graph it. How to graph. Step number 1. You completely factor. You completely factor f of x, all right? Be careful to group any like factors, all right? This is step number 1. Step number 2 is you identify your X-intercepts. Let's say C1, C2. Let's suppose that there are R of them, all right? And then you take those and you put them in order on a number line, all right? All right, put them on order in a number line, and then you add pluses and minuses as appropriate. And so that's the part you guys are super fuzzy on, about half of you. The other half, get it, and you did it right, fine. You know, and I'm using half as, it's not scientific. I haven't done a careful study, and there's 50% each. I don't really know. Just my impression of all 4 sections of college algebra as a whole. Maybe all of you guys get it. No, that's not true. Like, it's just statistical impossibility. So some people understand, some people don't yet. We're going to work on that today. So you add pluses and minuses as appropriate to the sign of the f of x, right? And then once you've done that, you graph. And that's pretty much all there is to it. Let's do it. So, like the first 2 or 3 examples of this that I'm going to do, I will underemphasize the trouble that's contained in point number 1. In other words, I'm going to graph examples where it's pretty much already factored for us. All right? And then as time goes on in here, I will circle back and look at examples where the factoring is more and more trouble. All right? Because we need to work on factoring. Almost everybody in here needs to learn more about factoring. Yeah? So, see, this is the blessing and the curse of math, which is that, you know, other disciplines have prerequisites, right? And what are the prerequisites for? To do what? To like keep you out of the class with the cool kids, right? I mean, truth be told, that 300 or 400 level discussion class, you'd be okay in there if you hadn't had the 100 or 200 level prerequisite for it, right? You're just not allowed in there because it's a means of crowd control, right? You have this batch of students, you want them in this class. You have that batch of students, you want them in that class. We are not so frivolous with our prerequisites in math. Like, there is a prerequisite because we use it a lot, and not knowing the prerequisite hurts you. That's why we have prerequisites. It's because we care. And unfortunately, there's no like, prerequisites should like evaporate, right? Like, it should be like, there's like a time delay fuse. Like, you have the prerequisite for math class. They should like set off like a 2-year timer. After 2 years, that prerequisite should evaporate for most people, because after 2 years, most people have forgotten it. So while you have the prerequisite on paper, in practice, you've kind of lost it, right? I mean, you guys are feeling that because a lot of you had high school where you did math the first 2 years, and then the last 2 years, you didn't do math. So now you're feeling the pain, yes? Yeah. So there's no way around it, right? We just have to. That's part of the reason I have policies like, you know, replacing your test grade with the final exam grade, because I know that you're just rusty, a lot of you, and you will improve. So do not despair. Do not give up. And also, if you're stuck on something particularly, don't feel bad to come to my office hours. I can help. Yep. Oh, that was not a, okay. Example 1. So let's graph y equals to f of x. And this f of x I'm going to give us as, let's say 3 times x squared minus 4 times x squared minus 3x plus 2. We'll start with this. So I said there's not much trouble. I violated my terms and conditions, what I said about 3 minutes ago. You know, I said we wouldn't have to factor. Okay, fine, we have to factor this a little bit, but it's not too bad, right? Like you can factor x squared minus 4. That's x plus 2, x minus 2, right? And you can factor x squared minus 3x plus 2. What's that? X minus 1, x minus 2, right? So we can factor these. Difference of squares. The other one is just kind of basic factoring, right? Now we need to take advice in number 1 carefully. Group any like factors, right? So what goes together here? See that? This guy and this guy, they belong together. So what we have here is 3 times x plus 2. I'll put the x minus 1 next, and I'll put the x minus 2 last. And the reason I'm going to do that is because I want to identify the x-intercepts in order, just, you know. So what are my x-intercepts? I have x-intercepts minus 2, 1, and 2. Right? Minus 2, 1, and 2. Now what? Now we make a number line. So the number line, here it is. I put my minus 2. I put my 1, and let's see here. 2, perhaps. All right. Oops. Here I'm putting f of x as my. All right. So here's a convenient trick. I'm going to start from the right and work my way left. That's just it's a nice rule of thumb for these problems. So here, by the way, what's the leading coefficient in all this mess? How do you figure out the leading coefficient? You're like, you have to multiply all that out, right? Well, you don't really need to do that. To get the highest term, you just take the highest power from each factor and multiply them. So like this, if you multiply it out, is going to be 3 times x times x. This gives me an x squared. So the leading term here is actually 3x to the 4th. All right, so my leading term is 3. And so that means that if you make the x big enough, it's going to be positive. All right, so the leading coefficient is positive, so we start with pluses over here, right? Alternatively, of course, you could try plugging in 3, right, and see that it's positive. Now what? All right, now I'm going to use the sign flip theorem to get the rest. So watch this. At 2, this corresponds to x minus 2 squared by the factor theorem, right? And at 2, we have a square, so we don't change signs. All right, so we keep it plus. In contrast, when we get to 1, that corresponds to this x minus 1. So there, we flip from plus to minus. All right? Now, at minus 2, that corresponds to x plus 2. Again, this is an odd power, namely 1, so we flip the signs again. All right? And that's it. Now, of course, you can double check things, right? Like, what is the y-intercept here? So that's f of 0. What is f of 0 equal to? I mean, I can't just read off the a naught like over here, right? It's not the standard form. I can't just read off this. I have to just plug 0 in and see what happens. Yeah, that's all to it. So I've got 3 times 2 times minus 1 times minus 2. Careful, that's squared. Yeah? So that's what? That's, what do you got? Minus 8 times 3, I think. I got a minus 24 if I did my math right. My y-intercept is minus 24. Does that make sense? Does that double check my number line? What should we have? Where is 0? Where does 0 live in the number line? 0 lives between the negative and the positive, right? It's up in here. 0 is right in here. Is it supposed to be negative? The value of the function is supposed to be negative? It is. Good. Double checks. Most of you need to double check your number lines. Okay, so anyway, so here's the graph. We did step 1, we did step 2. Now we're into step 3, graph. All right, so how do we do that? We use the number line. The number line, again, has recorded on it where the X-intercepts are, right? So my X-intercepts are at minus 2, at 1, and at 2, right? And so here, I'm not trying to graph both axes to scale or anything like like that. I'm just kind of following the pluses. So it starts out positive, right? And then what's it doing? It crosses through minus 2 like that, right? And then it's crossing through 1 again. So it has to come down. It has to turn around, right? To go back through 1, right? It goes back through 1. And then it comes back to 2. But what happens if it stays plus on both sides? What I like to say is if you're going plus to plus like that, I like to say that the graph bounces off the x-axis. So it bounces like this. Boing. There you go. So bouncing, so basically here's the deal. If you've got a factor which is odd, that corresponds to your graph crossing the x-axis. If your factor has a power which is even, it bounces off the x-axis like this. Any questions? And there you go. That's the graph. And I can be a little bit more precise. What's the y-intercept right here? Minus 24. So there you have it. This is y equals to that. So my point to you is if you already understood the nonlinear inequality material, this is really not much different, right? It's just you draw the number line just like we did before, and now make the picture, right? Before I said things like it bounces at this kind of critical number, we called it. But now we understand, hey, that critical number is actually an X-intercept, and I literally mean bounce off the x-axis. Something similar will be true for rational functions, but we'll get there when we get there. Okay, so example 2, unless there's a question. Let's graph y equals to f of x equals to, let's say, x cubed, and then I'll do x squared minus, let's say, I don't know, 7 quantity squared. So this one's a little bit annoying because it's got the x squared minus 7, right? We need to factor that. How do we factor x squared minus 7? We do what? We do x plus the square root of 7, x minus the square root of 7. Now all of that is squared. So how does that work? When you have all of that squared, how does that go? So what that's going to give us is x plus the square root of 7 squared. I'll put the x cubed in the middle, and I'll put the x minus root 7 squared over here just to... You can put them in any order you like. I just put them in that order to put them like I want them on the number line, that's all. You don't have to do that. The larger point here is that when we have a product that's squared, it's just the square of the things multiplied, right? So if I have like, pattern I'm using here is if I have ab squared, right? That's a squared, b squared. So I'm thinking of x plus root 7 as a and x minus root 7 as b, and so give me the a squared and the b squared. All right. What are my x-intercepts? I have one at minus root 7. What is x cubed? What does that mean? What x-intercept does that give us? What do we do with the x cubed? Where's that put us? 0, right? That's the x-intercept of 0, because that's x minus 0 cubed. And then you got square root of 7. So make your number line. I'll put 0 in the middle. And minus root 7 and root 7 out here. All right. All right, so this one, again, the leading coefficient is what? If you look at it and multiply the biggest thing in each one of these, you've got x squared, x cubed, x squared again. So the leading coefficient here is 2 plus 3 is 5, is x to the 7th. Right? By the way, I meant to say this in example 1. We said that the leading coefficient was x to the 4th, 3x to the 4th, right? What did the big picture of the graph look like here? Notice it was like, if you were way away from this, you wouldn't see all these wrinkles, right? It would just look like a big bowl going up. It would look roughly like this, because it's an even power with a positive coefficient, right? This one here, it's a odd power with a positive coefficient, so we expect the graph of example 2 to, roughly speaking, look like this. Okay? Anyway, the sine chart, we've got pluses here to start with. And then what do we do? At square root of 7, right? Which is what? What is the square root of 7 anyway? It's about 2.65. Yeah, that's kind of not even terribly relevant, but anyway, just give you a sense of it, about 2.65. Now, at square root of 7, do we change signs or maintain signs? And why? As we go across this x-intercept, this critical number. See this right here? X minus root 7 squared. That means we bounce on the graph. So we keep the pluses pluses. Going across root 7. Going from right to left again, starting with plus, going across here. My x is coming from x, 0 is coming from x cubed, right? That's an odd power. That means we flip from plus to minus. All right? Now we're at minus the root 7. The question is, what happens here? We go back, we look at x plus root 7 squared, right? Even power. It bounces on the graph here again. So we stay negative. So the sign flip theorem is about how to change the sign going from one case to the next. All right? So how do we change the sign or not change the sign as it happens? Okay, we got everything we need to graph. Let's do it. Put in my x-intercepts here, here. Well, what about the y-intercept? That one's kind of funny here, isn't it? The y-intercept is the x-intercept. It's the origin, right? And what happens? We're negative, right? Negative. What do we do at minus root 7? What do we do at root 7? We bounce both places, right? So we bounce off the x-axis here. Bounce, right? And then we have to turn around somehow. We have to come back through the x-axis at 0 because we cross at 0, going from minus to plus. Yeah? Then we have to somehow turn around again and bounce off root 7, and then go on our merry way up here, like that. Again, if you zoom out from a million miles away, it just looks like this picture. Roughly speaking, it should be going to minus infinity as you're going way, way to the left, and it should be going to plus infinity as you go way, way to the right. So in your homework, they've got these crazy arrow pictures with like the arrows cut off in the middle to try to illustrate this idea. So my arrow pictures, I just don't, like the book, for whatever reason, feels the need to erase the middle part so that you guys won't get confused and go, oh, but it doesn't have this. And it doesn't have this, so it's not that. You know, like I say, my way of saying that is a million miles away. You're not going to see this wrinkle. all you're going to see is the big part. So, any questions? All right, let's move on. Oh, I hope you top hatted. Sorry. Oh well. Anybody here not top hat? No? Okay, good. Let's see here. Another example. Let's say minus x plus 10 cubed times x plus 5 squared times x minus 3 to the 4th power times x minus 8, just like that. And let me trade that minus up for a minus 2, just so you can see it better. Okay, so let me start here by what's the leading term? What's the leading term in this example? Oh no. I think I forgot to move the camera over. No! Oh well. Well, you guys are here, right? The good news is if you watch, well anyway, I have tried to do different examples, a little bit different examples in every section. So if you watch the videos from Monday, you'll see different examples in every section pretty much. So if you thirst for more examples that are all the way on the video that you want to watch, I would encourage you to look at sections 1 through 3 yesterday. There are oodles of examples there to be seen. But anyway, here, the leading coefficient, we got our minus 2 from this, yeah? This gives me an x cubed. The biggest thing in there is x cubed. The biggest thing in here is x squared. The biggest thing in here is x to the power 4. The biggest thing in here is just x. So, in other words, to get the leading coefficient, you just multiply the biggest thing in each factor to get the leading coefficient, right? And so what that gives me is 3 plus 2 is 5, plus 4 is 9, plus 1 is 10. So I get minus 2x to the 10th. So the degree of the polynomial here is 10, okay? Now this one is easier than the other one we did, because there's no factoring to do here, right? It's already factored for us. Yeah? So we can go straight to the X-Intercepts. What are they? We've got minus 10, minus 5, 3, and 8. Those are your X-Intercepts. And so make sure you put them in order on the number line. Start with minus 10, go to minus 5, 3, and over here 8, roughly speaking, all right? Now, what do we have, pluses or minuses? If we're a really large positive number, what happens? So the leading term dominates, so we get minuses to start with on this one. If again, I'm going from right to left. If you want, you can plug in 10 to this formula, and you can see it's positive. All right. But the positive is multiplied by minus 2, which makes it altogether negative, right? So, like I said, plug in 10 if you want. Here you get plus, 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 and then that minus 2. So altogether it's negative. All right. Now I get to 8. Do I flip signs or do I stay? See, the X-intercept of 8 is coming from the x minus 8 factor, which means I switch from minus to plus. Right? Minus to plus. Now I get to 3. What's 3 coming from? 3 is coming from this x minus 3 to the power 4 factor, right? That's an even power. That means we bounce. So we stay plus. All right? We get to minus 5. What happens there? That's from x plus 5 squared. Again, even power, we bounce. So we stay plus. All right? Then we get to minus 10. Minus 10 is coming from this x plus 10 cubed term. That's an odd power. That means we cross the axis there. We switch from plus to minus. All right? Let's double check our work. Let's check one of the middle cases in this one. All right? I think that's probably a good practice for you guys. Double check your sign chart somewhere. In this case, I'm going to check the Y-intercept. That would be f of 0. What is f of 0 here? It's minus 2 times 10 cubed. Whoa, it's big. Times 5 squared times minus 3 to the 4th power. I think I'm going to need my calculator. Times minus 8. So whatever that is, that will be my Y-intercept. Let's see here. Minus 2 times 10 to the power 3, also known as 1,000, right? Times 25 times 3 to the 4th power is actually 81 times minus 8. Whoa. Yowzers. So if I haven't made a miscalculation, I believe we have, I'm having trouble counting the number of zeros in this thing. 32,400,000, I think. And it is positive, right? Because you have a negative and a negative on the outside, and this negative to the 4th power is plus again. So you got minus, it is a positive. Positive 32,400,000. Wow, that's big. Does that check my sign chart? What do you think? Where is 0? 0 is where? 0 is between minus 5 and 3. We're supposed to find positive value. And we did. This absurdly large number. Obviously, you don't want to try to graph these things to the same scale on x and y, right? You're not going to see it, are you? So here we go. Let me graph this thing. We've got minus 10, minus 5, 3, and 8. All right. Sometimes I graph right to left. Sometimes I graph left to right. I've done left to right the previous times. I'm going to do right to left this time. So I start out negative, right? And I cross through 8. So I start out negative. I cross through 8. All right. And then what happens? I come back, I bounce off 3, all right? And then I come back and I bounce off minus 5. And then I come back and I go through 10 like that. So there you go. That's the graph y equals f of x, roughly speaking. And of course, not to scale by any means, right? Because the y-intercept here is what? 32,400,000. Yeah. But this is a good indication qualitatively of what the graph looks like. Right? It bounces at minus 5. It bounces at 3. And altogether, it looks like a big bowl that opens down. Right? That's the million miles away way of looking at it. We're in, this case over here. All right. So we have another example to do today. The last example that I have to show you, it is going to open up a new can of worms, if you will. There's something else for graphing that we have not yet explored. There is another tool in our toolkit that you should know about that we have not really said anything about, really. I don't think I've uttered a word about it up to this point. But it's an important technique for graphing. And it does, in some sense, go hand in hand with the